Hi, my name is Shahnawaz. Uh, so far, we have discussed morphisms. Let us quickly recall what do we mean by a morphism. So, suppose we are given two varieties, say x and y, and suppose we have a map phi from x to y. Then we call this map phi a morphism, or sometimes we call this a regular map. If this phi is continuous, so phi has to be continuous. And uh, phi has to preserve, phi must preserve regular functions. So phi must preserve regular functions. That means uh, phi star of f, which is same as f composite phi. So it has to be, regular on, the inverse image of u for any open subset u of y. So this u is a subset of y, it is open subset. So this map phi star, which is a map from the regular functions on u to regular functions on phi inverse u. So this is called the pullback. So if this phi satisfies these two properties, we call this map phi a morphism. Now we want to describe these morphisms in a more explicit way. So first we do this for morphisms to subvarieties of an. Uh, I mean, um, um, these morphisms, they are just given by n tuples of regular functions when we consider morphisms to subvarieties of an. So we have a theorem here. So it states that, so let us consider two varieties, two subvarieties. So let x and y be varieties, and assume that this y is a subvariety of an. So a map, say phi from the variety x to y. So this is a morphism. Uh, if and only if there exists, if and only if there exists, regular functions, say f1 up to fn. So it depends on this n here. Uh, so these are the regular functions on x, on whole x, with phi of p given as f1 of p up to fn of p. So this has to be true for all p next. So thus a map p from a variety x to y is a morphism if and only if it is given by an n tuple of regular functions. So this is what we have to prove. Now let us first assume that this phi is a morphism. So let phi from x to y be a morphism. Now let us consider say y1 up to yn. Let us consider these, I mean, regular functions which are, so this is y here, which are given by the restrictions of coordinates on a and to y. So these yi's, they are the restrictions of coordinates on a and to y. That means any yi when I mean evaluated at some point of an gives the ith coordinate of that point. So that is uh, if we evaluate yi to some point of an, so or let us do this way, that is if q, which is some point in an, so let us call this a1 up to an, so this is a point in an, then when we evaluate yi at q, it gives us the ith coordinate of q, which is ai. So obviously they are regular functions on whole y. Now let us put, so let us put fi to be the pullback of uh, yi. Now yi being regular on y and phi being a morphism, that means this phi pulls back yi to I mean this p pulls back this regular function to a regular function, so which is by definition equal to yi composite with phi. So this is regular on x because this phi is a morphism. So and these yi's are regular on y. So since the reason is that yi is regular on whole y, so this phi pulls back these regular functions to regular functions because we have assumed that phi is a morphism. So this is, and the reason that phi is a morphism. Now let us consider some point p in x. Now we have to show this phi is given by an n tuple of regular functions. So note that these phi i's are f i's are regular functions. So let p be any point in x, and suppose phi of p, which is some point in n, suppose it is equal to b1 up to bn. Now this being a point in y, so this is a point in y, so we can use these coordinate functions. So these vi's, they are given by the coordinate functions. So then each bi is actually the is actually given by the coordinate function yi evaluated at the point I mean evaluated at the point b. Let us call this b. So let us call this b, where b is the point b1 up to bn. So this yi when evaluated at b gives the ith coordinate of b, which is bi. So this would imply that is, or so this implies um, this bi is actually uh, yi. Now this b is same as phi of p, which is same as, because yi composite phi is fi. So yi composite phi is fi. So this is fi of p. So hence phi of p, which is given by this n tuple b1 up to bn, and each bi is given by fip. So we can write this b1 as f1 of p up to fn of p. So we proved here that if phi is a morphism, then this phi is given by this n tuple of functions f1 through f1, fn. So one can note here these fi's, they are regular functions, because each yi is regular and this phi is a morphism, hence regular. So this is regular. Now conversely, assume that this phi is given by an n tuple of regular functions. So we have to prove phi is a morphism. So conversely, let this phi is given by an n tuple of regular functions. So with these fi's, they are regular on whole x. So they are regular on whole x. So that is phi of p is, so that is phi evaluated p is f1 of p up to fn of p. Now to prove phi is morphism, we have to prove phi is continuous and it preserves regular functions. I mean, it is compatible with regular functions on open sets. So now to first prove phi is continuous, it suffices to prove phi pulls back closed sets to closed sets. So for that, let us take some closed set in the variety y. So we first prove phi is continuous. Now for that, let us take some closed set in side y. So let b subset of y be closed. So here by closed we mean it is closed with respect to the Zariski topology on y. So be a closed set in y. So therefore we can write this b as, so therefore we can write b as the intersection of, I mean, it is the zero set of some polynomial, say g1 up to say gn, intersection y. So we take intersection y here to make it clear that this set b lies inside y. So these gi's are some polynomials. So where gi's are in the polynomial ring in n variables, because this y is the subvariety of an. So this is true for all I equal to 1 to n. Now let us pick some polynomial among these gi. So let G be an element in the set in G1 up to Gm. So we are picking any polynomial among these m polynomials. So we can write G as, so we can write, so now G being a polynomial in this polynomial ring, so this is actually the sum of with coefficients a, say I1 up to in x1 to the power I1 up to xn to the power in. So this sum runs over these and I mean over these elements I1 up to in. So now let us look at the map. uh, I mean the function G composite phi. So G composite phi is actually G, and phi is given by this n tuple. So this is f1 up to fm. Now G evaluated at this m tuple is actually a polynomial in these fi's. So this is same as G sigma ai1 up to in. So this is f1. So we had to switch these variables x i's with f i's. So this is I1 here. So up to in. So one can note over here this is a regular function on whole x, because these fi's they are regular on x, and this is the linear combination of these regular functions. Now this ox of x being a k algebra, this means that this expression is inside x. So the reason is that because ox of x is a k algebra. Now to prove phi is continuous, I mean to prove this phi is continuous, we have to prove the inverse image of this closed set B is also closed. So now phi inverse B is the set of all points in X whose image lies inside B, which is same as the set of all points in X. Now phi of B being in B means that phi of P lies inside the zero set of the polynomials G1 up to Gm. So this is same as the set of all points P in X such that now phi of P is inside the zero set of these polynomials if and only G1 of G1 computed phi of P is 0. I mean, so this is inside 0 if Gi of phi of P is 0 for all I equal to 1 up to m, because this phi of P, now if phi of P is inside this set, that means each Gi evaluated at this point, I mean phi of P is 0. So that is what I write here. So this is same as the set of all points in X such that this P lies inside the zero set of the polynomials Gi composite P. So I mean G1 composite phi up to Gn composite phi. Now to make sure that this set lies inside X, we take intersection with X. So one can see that this is a closed set in X. So hence, which is a closed subset of X. So hence phi is continuous. Now to prove the second part, I mean to prove phi preserves regular functions, we are going to pick some regular function inside y. So let v subset of y be open and let h be a regular function on v. Now we have to prove that phi star of h is regular on the inverse image of v. So we write so put w equal to the inverse image of v. So we have to prove, so we have to show that the inverse image, sorry, we had to show that the map H composite phi, I mean this function is regular over the inverse image of v, which is w. So this is what we had to prove. So since we can write h locally as quotient of polynomials, because this h is given to be a regular uh, on, I mean v, so this regularity being local property, we can say that. So let q be any point in v, then there exists a neighborhood, an open neighborhood, say u of q, such that uh, in this neighborhood we can write h as the quotient of two polynomials, such that h of s is the quotient of the polynomials, I mean h of s is the quotient of fs or say gs for all, so for polynomials f and g with g non-vanishing on pole u. Now let us consider the map p star h of t. So we know it is h composite phi of t. So h composite phi of t is given by, so this is same as h of phi t. Now h of s is like this, so this is f of phi of t over g of phi of t. Now this is same as f of, phi of t is, phi is given by the n tuple of regular functions, so we can write this as f1t up to fmt over not m, I mean this is n here, over g of f1 of t up to fn of t. Now note that the local ring at t is a k algebra. So as the local ring at t is a k algebra, then these two functions, I mean the function f of f1 up to Fn, and the function g of F1 up to Fn. So they belong to the local ring of T, and this g of F1 T up to Fnt is nowhere 0 on T. This T is inside U. So this means that this function g of F1 up to Fn is a unit in the local ring. So thus g of F1 up to Fn is a unit in OXT. That is, that is the function phi star h is regular in this local ring. So this is for all t inside W. So that means hence phi star h belongs to, so since this is true for all W, so this belongs to the local ring or on W. So this proves the theorem. Now we have a small corollary here. So a regular function f which is regular on whole x. Now x is given to be a subvariety. So is same as the morphism, is same as the morphism phi from x to the affine one space. So this follows immediately from the above theorem.